In this chapter, we are going to talk about query processing and query optimization. As the name says, the query optimization is a process of writing the queries in a way such that it brings out the results out of the database in the optimized way. By the word optimize, we mean that how faster, how better you write the query, that much faster the results are produced by using minimum resources from the RDBMS. Now, this whole process requires you to have knowledge about the relational algebra and the different canonical forms that can be produced by using relational algebraic expressions, okay, for a given query. What does all these things means? It is as simple as to understand that, for example, if you want to reach to my office from your classroom, there are more than one ways to do that, right? Some of you would might take the elevator and come to my office directly from the ground floor to the second floor. However, some would try to take the stairs to come to my office. Some would come from a longer way. Some would come from a shorter way. By this, we understand that in order to reach to the destination or in order to reach to, the result, you have different ways of solving the problem. Similarly, if you write a query in SQL, it can be translated into different relational algebraic expressions or in different query trees. Okay, so by this we mean for sure that there are different ways of writing a query and solving a query. The query optimizer, which is built inside the RDBMS, will select the best query based on the less number of IO reads that it has. So similarly, if you are taking the example of you reaching to my office from your classroom, you are going to take the best way. There are, for example, 4 ways to reach to my office, but you are going to write all these 4 ways, and then you're going to calculate which one is taking less time, less number of steps, and you're going to reach me. You will pick up that way and then you execute it. Similarly, given an SQL query, you have more than one ways of writing an algebraic relational expression for it. And this is what we are going to see in throughout our today's discussion. There are certain rules that we follow in order to write the relational algebraic expression for a given SQL query. And if you understand that one, you would be easily able to solve the questions in the final exam given in this way. For example, you would be asked to draw at least 2 query trees that can represent each of the given queries, okay? And under what circumstances you will select the best one. Okay, so an SQL query will be given to you and you are going to write a relational algebraic expression for it. And then you are going to draw the query tree. Okay, so this is the answer that you will give. Okay, you see? Okay, now I want you to just pay attention to how the question will be asked and how the answer looks like. The question will be, asked for you by giving a SQL query. You will be given an SQL query, okay? And then you are going to draw the query tree for it and select the best one, okay? We will solve this over time. Don't worry, we have all these many slides coming to explain us to get the answer, okay? So this is the question. This is the part of the question. You are going to work from here. Relational algebraic expression you will give. You will draw the query tree. You will draw the another query tree and you will select the best one. Okay. So this is how the question will be asked from these particular slides. I don't want to explain anything right now. Okay. Because it will be too much for you. So let us understand the whole lecture first, all the slides first, and then we come back again to this and solve it. Okay. Now, motivation for the query optimization. As we said that, there are more than one ways of executing a given query, right? So here we have a query which is asking us to list all the managers that work in the sales department. So our aim is to pick up the manager names, okay, who are working in the sales department. The manager names are available inside the employee table, and the department names are available inside the department table. Hence, we are writing select star from employee table, comma department table, where employee department number is equal to department number. Now, this is very important. This is called as predicate. Now, predicate is going to help us with the where condition. Now, what is happening? We have a different employee table. We have a different department table. How they both are connected? They are both connected with the foreign key and primary key. For example, we have a department number as a primary key in department and working as a foreign key inside the employee. So when these two values are same, it means the employee belongs to the same belongs to that department. For example, we have department number as 101, okay, for a CS, 102 for IS, okay, and we have instructor ABC, okay, with the department as 101, and we have AAA with the department as 102. Okay, so now using this 101 in the employee table, I am going to, connect the row details like, the name of the department, okay, and the location of it inside the department table. So it's like you have an employee table and you have a department table, okay, and then here I have department number, which is going to connect to me to the department number in the department table. So the value, if I have 101 here and I have 101 here, so it means that I can take the name of the manager from the employee table and take the name of the department for the department table. This is my employee table. This is my department table. Okay, so this is the use of the predicate. Predicate is actually helping us with the where condition. Okay, now it is very important for us to understand how we write the where condition inside the relational algebra. We use projection for this. We use, projection. We use, combination of row and projection. Projection is helping us to get these things. Okay, so for selecting, I will use projection. And when we have a condition, I will use the row. Okay, so this is called as projection. This is called as row in relational algebra. Now when I'm going to translate this SQL inside my relational algebra, I will make use of projection. I will make use of row and I will use of projection. That is the need why I have quickly overviewed you everything. Okay, so now let me clear it. Okay. As you see here, we have some numbers, this number and this number and this number. What does it mean? It means that the same query can be written in more than one form. Okay, now each query, each algebraic version of this query will have certain write, record numbers. Okay, as you see here we have almost 101, 1 lakh of record IOs. And here we are having 3,000, and here we are having only 1,100 approximately or 1,200 IO records that are doing the same work. For example, now if you want to reach to my office, okay, from your classroom, there are many ways. Okay, the one is, here is very big. You need these many steps. Here you need 3K steps, and here you're needing only 1,100 steps. Which one will you follow? Of course, you will follow the smallest one, this one, right? You will follow this one. Okay, so similarly, this query can now be written in at least 3 ways, okay, by using relational algebraic expression. Okay, now let us see the first one. The first one is, you are saying select me the rows where job is equal to manager and name is equal to sales, and connect these two tables by using the Cartesian product. Okay, so it is going to give me the names of all the managers who are working in the sales department, okay, by connecting these two tables. And this is the predicate, okay, the simple predicate you put. How are we, okay, again, I will explain you how are we going to translate this SQL into the relational algebra. Wherever we have select for the rows, okay, this condition, this is our select condition. So we are going to write down select job is equal to manager. This and is represented with an intersection. Okay, name is equal to sales. Again, the projection for the row for it. Okay, select with condition. Select with condition is nothing but our row. So that's why we are writing a row here. Are we understanding? Select with a condition is always coming with a row. Okay, so select me all those details, all the details where job is equal to manager and name is equal to sales. Okay. Okay. And and what? Do this when the department number inside the employee table is equal to the department number inside the department table. Okay, for the example that we discussed. So it's like going to give me the name of the manager, name of the sales that we just discussed in the slide in this one, right? And we are going to connect these two tables, employee and department tables, with the Cartesian product, also called as the cross product. Okay, so in a relational algebra, you can connect two tables by either using a Cartesian product or by using a join. So this query is written by using a Cartesian product. Okay, done. Did you understand this first? Okay, now, now when we are executing the given SQL query by using this relational algebraic expression, the total number of the read and write records is exceeding 1 lakh records. We will see how all these things are happening after a while. At this particular slide, I just want you to understand that given SQL query can be represented in many forms of relational algebraic expression, and this is the first one. I hope you're getting the point. Now let us see the second way. Okay, so I will clear. Okay, now let us see the second way. This is another way of rewriting the SQL query in another form of relational algebraic expression. As I told you, there are two ways to join two tables. Here we are joining two tables. Here we are joining two tables in SQL. In relational algebra, the tables can be joined by using a Cartesian product or by a join. Now, the second query we wrote by using a join, which is only taking 3,000 record IOs. It means only it is accessing 3,000 approximately records to get me the name of managers and who are working in the sales department from these two tables, employee table and the department table. You see, there is a tremendous decrement on the number of IOs when we use the first relational algebra, and then we are using the another relational, algebraic query. So, which is the better one? Is this the better one, the first one, or is the second one better? Of course, the first one, second one is better in these two cases, right? Okay. Now, let us see the third way of representing this SQL query. Okay. So, okay. Now, this is the third one. Here, we are selecting job is equal to manager from employees. Okay. And we are connecting the employee table with the department table and selecting only the department whose name is equal to sales. Okay, so using the join again. Okay, using the join again. So what is the difference between the second and the third? What is the difference between the first and the second? Instead of using a Cartesian product, we use the join, which decrease the number of record IOs by 10 times. And here we have more than 1 lakh IO records. Here we have only 3,000 IO records. Now the second and the third, now more advanced relational algebra is algebraic expression is given for the same SQL query in the third case, wherein we are first selecting only managers, okay, and only the sale departments, and then we are connecting it. So it's again further reducing the IOs by, half of it, more than half of it, one third only. So now we have only 11,060 record IOs. So if I ask you that this is my query, these are the different ways in which I can represent my SQL into relational algebra. And when I execute them, the first is taking this much of work, the second is taking this much of work, the third one is taking this much of work. Which one is the best, you think? Of course, this is the best one. The last one is the best one because it is having less number of IOs. This is the motivation of using the query optimization. With this, what did we understand? We understood that an SQL is given, which can be represented in different number of relational algebraic expressions, and we select the best one out of it. Now, the next discussion is how did we know that this first relational algebraic expression for a given SQL took this much of record IOs? And how the second one is taking these many IOs and why the third one is taking very less. So this is our discussion throughout the chapter. Now, with this understanding, can you now solve a part of this question? Okay, it is asking us that draw at least two query trees. Okay, two query tree will come after a relational algebra. We know how to translate the given SQL into the relational algebra. Wherever we have a select predicate, this is our select predicate, it will be given by row. For example, you see here we have P dot the department number D dot D number. So we have it here in a form of, yeah, P location Stanford. You see P location Stanford. Okay, and then we minimize this here and here. We are, trying to link these two tables, and we are, using a join to do that. So done. And what do we want to select? We want to select the P number, department number, last name from the employee, address, and B date. So the select is nothing but selecting the columns, which is represented in relational algebra by using a pie. So we translated SQL into relational algebra. This is, half part of your question is solved. If this question is, for example, asked in 5 marks, then you get here 2 marks for translating the SQL into the relational algebra. Did you get my point? Great. Now, let's move. Now, this is the next step that we are going to see after discussing the second half of the chapter. So I will not explain you right now. Just I'm going to tell you that here you see we have a project table, department table, and employee table. Here we have project table, department table, and employee table. And actually we have these tables to take the values out of it. Okay, for example, from project, department, and employee. And the query is having project, department, and employee. Project, department, and employee. That's it. Just understand the leaves from this big tree. Okay, and we are going to discuss about all these things after some time. Okay, so erase all of it. Okay, now let's move here. Erase all the link. Okay, and we discuss about these three ways of representing the given SQL query in form of relational algebraic expressions. Okay, now let us take the first one. In the first query, we are saying that we want to select all the employees who are working as manager, okay, in the sales department. Okay, so that's why we said select job is equal to manager. Okay, and he is working in the department as sales, department name as sales. Okay, get me all these things. But before that, make the Cartesian product for employee and department. Now, making a Cartesian product is a huge work. For example, okay, a quick recap of how the cross product or the Cartesian product works. Now, the Cartesian product is you have one table, okay, you have another table, and you want to make a cross product of it. So, what will you do? You will have a bigger table now. Okay, you will create a big table wherein you will have this first row. Okay, it is a cross product, right? For example, you have 1, 2, 3 rows in the first table. Okay, and then you have 101, 102, 103 in the second table, and the Cartesian product is made like this. So 1, 1, okay, and 101. And the second entry is 1 with 102. And the third entry in this table is 103. Then 2 with 101. Then 2 with 102. And 3 and 2 again with 103. Okay. And then 3 with 101, 3 with 102, and 3 with 103. So this is this is called as the cross product. Okay. So how many entries that we will have here in the big table after making the Cartesian product? We will have, for example, here 2 and here 3. Then it means we are going to have 2, 3, 6 entries here. So here, 6, 1, 2, 3, 4, 5, 6. Now, if you have, for example, if you have it, for example, 100, 1,000 tables in the relational, in the employee relation and 50 tables in the department, then the cross product will create another table with how many rows? 1,000 rows multiplied by 50. So big, right? So these many IO records are actually created at this point itself, Employee 1,000, okay, 1,000, and uh, employee is having 1,000 rows. Rows are nothing but tuples, right? And department is having 50 rows. So here itself, we have 1,000 multiplied by 50 records created as a table. It's a big, overhead for checking all these tables, right? Many times, all the rows inside the table. Okay. So did you understand how the cross product works? Okay, next move. Okay. Cartesian product of employee and department is going to create, 1,000 multiplied by 50 records, and it will create an intermediary relation to store the results like this one. A big one it will create. Now, we know that there are 1,000 employees inside the employee table. Okay, so I will need to check all these 1,000 employees, that who of them are manager, right? Who of them are manager. So I will check the first one, I will check the second one, I will check the third one, and I will check all of them. Okay, so I will need to scan 1,000 records. Plus, there are 50 records inside the department table. Okay, then I will need to check all these 50 records to know which department is the sales department. So how many IO records in total needed here? 1,000 plus 50 plus 1,000 multiplied by 50. 1,000 multiplied by 50 because of creating this. Okay, and then inside this, I need to check 1,000 times in the employee tables because there are 1,000 employees inside the employee table and 50 for the sales table. Okay, so this is our Cartesian product, only the Cartesian product. Now we have to do and this and this. So selection on the result of Cartesian product, we now need to check again here, right? How many of them? So this is, how many records are inside this? 1,000 multiplied by 50. So we have, this 1,000 multiplied by 50, this 1,000 multiplied by 50. So we need to do this work 2 times. Once you create, then you check. It's like, once you're creating a table of 100 records, then you are checking all the 100 records. So here we have 1000 multiplied by 50. This is 5000 records you created here. And then you're checking 5000 records. That is why you have to write 2 multiplied by this. Plus how many rows, number of rows in the employee? 1000. How many rows inside the department table? 50. So this is how we get 1000, 1 lakh, 1000 and 050 records. This is how you calculate the cost of processing of the query alternate. This is your second part of your question solution. Here we are saying, we are asking you, right, what are the different ways of writing the SQL query and how do you calculate the cost of processing? So you calculate the cost of processing depending on the number of IOs. Reading records, how many records and how many times you have to read the record. So this is the way how we calculate the cost of processing. You can pause the video here, work out this exactly the same way in the paper and relax for a minute because you're going to do the same thing for the next query alternate and the third one also. So I want you to take a break here. Okay, just pause 2 minutes and then just do it on the paper. For your understanding, I have written all the points in the slide notes. You can check them. Okay, now let's move on to the next alternate. Now, we said already that joining of table in relational algebra can be done in 2 ways. One is by using a cross product, another by using the join. Here we are using the join. Join is much easier. As you see here, we have one table, a quick recap of how the join works. We have a student table, we have a course table. And if we want to join them, okay, for example, we join, the 11th row because we have an 11th row here. And we have, for example, yeah. So if you want to join the student table with the course table and you want to know the name of the course for a given, course ID, okay, you will join only those records which are having the common predicate or common, foreign key and primary key value. Okay, so if you see here, we have 3 rows here and we have 2 rows here, 3 rows and 2 rows. But how many do we have in the join which satisfied the condition? Only 2. So if you remember, when we were doing this job by using a cross product, we have the total number of columns, a total number of rows selected was, 1000 multiplied by 50. It created an intermediary cross product table out of after cross producting this one. But here we have very less, very less. You see here we have, for example, we have 10,000 rows in the employee table. Here we have only 50 rows. Now we are going to only take those row numbers and create a new table which is satisfying the condition. So it is very less. Okay, now how to do that? Now here we have selected job is equal to manager. Okay, and select the department whose name is equal to sales, and then connect these 2 tables when the department a number inside the employee table equals the department number inside the department table. Foreign key and using foreign key and primary key, equating them, we connect the tables, right? We connect this table and this table. Okay. So now here we have to join. Okay. So now we know that we have 1000 rows inside the employee table. Okay, it will check all 1000 the records for knowing that who is working as a manager in employee, and 50 tables from the sales. So 100 plus 1000 plus 1000 plus 50. Okay, record IOs plus 1000 record IOs to create an intermediary relation store in the join. Okay. So maximum there will be how many intermediary relation? 1,000, because we have the employee as 1,000. So now selection on the result of join. So out of these, you will only select 1,000. So here we have this 1,000 and this 1,000. So 2 multiplied by 1,000 plus how many rows you have to check in the first table? 1,000 rows. How many rows you have to check in the department table? 50. Why? Because here in the 50, 50 tables are in the department table and 1,000 rows are inside the EMP. So you have to check 1,050 rows in both the tables, and how many record IOs are there for the join. And checking in the join is creating me 1,000 records, and after you create the 1,000 records, you need to check 1,000 records. That is why we always write 2 multiplied by 1,000, or in our earlier case we wrote 2 multiplied by the Cartesian product. So this is the result from the Cartesian product. Okay. And this is the result from the join. You see a lot of difference, right? So that is why in the second way of executing the query, the number of IO records have decreased greatly, significantly. Decrease. Yeah, decrease significantly. Okay, now let us move to the third way. In the third way, what we are doing is we don't want to check all the rows inside manager, inside the employee table. We don't want to check all of them. We want to pick only those names whose job is manager. And how many managers do we have? We have only 50 managers. So don't check the first one, don't check the second one, don't check the third one. So it is not like a linear scan. Don't do the linear scan. Only select those ones which are managers. So we are actually not reading the entire table after joining. We are, because after joining we have 1,000 tables, 1,000 rows to check. After making a Cartesian product, we have 50,000 records to check. So what are we going to do is, before making this operation of cross product, before making the join, we want to select only those students or those employees who are managers. It is something like, for example, you are you are you are in section 61, your friend is in section 62, and I want to select the students, okay, who got GPA greater than 4. Okay, so there are two ways. I can mix the section 61, okay, section 61 and section 62 by using a cross product. Now in section 61, for example, if there are 1,000 students and section 62 is having 50 students, so after I cross product them, I will have 50,000. From this 50,000, I have to select, for example, 4 students who got GPA greater than 4, and here 3 students who got GPA greater than 4. I need only to select 7 out of them. So I created 50,000 using the cross product. I created 50,000 students using the cross product. I mix them in this way. Okay, and then selecting only 7. So it's like now I have to select 7 out of 50,000. So I have to check all 50,000 students. So before doing this cross product, or even before doing the join, you are first of all picking up this 4 students from 61 and 3 students out of 62. Okay, so it becomes a lot more easier. So now in the third one, what we are going to do is we are going to perform the selection first, then we are going to apply the join. Okay. So, okay. Now you see here, what is the difference? This is this. Okay, let me come to the first one. First slide where we have everything written. So now you see, students, how do we execute the relational algebraic expression? This is executed first, then this is executed. Okay, similarly, this is executed first and this is executed. But now here, what we did, we moved this part in the third query. We moved this part. What happened? Why did it happen like this? I want the previous way. Yeah. Okay. Why is this becoming smaller? Okay. So what did we do here? We have moved this part. The okay. So now let us see. This is the first thing that we execute. Let me take the pen. Okay. Then in the second query, we join. In the first query, we made the cross product first. Then we selected manager and this sales. And then in the second query, we joined both the tables. Then we selected manager and sales. But in the third one, we are selecting the managers first, which are only 50 managers. And then there are five departments out of 50 in the department table who works with the sales, who are named as sales department. So here we are selecting 50 and we have five managers, 50 managers working in five sales department. We are selecting this first. Then we are applying the join. So we have 50 plus 5 multiplied by join is how many? Join is giving us how many? 5,000. So you see here, uh, the third way. Here we have, this is the third one. Here we have 1,000 records of managers and 50 records from department table. So we select the managers in employee. We select the, yeah, out of 1,000, how many did we select? 50. Okay. And how 50 managers, and how many sales departments are there? 50 sales departments are there. How many we selected? 5. So what is important to us? This 50 is important to us. This 5 is important to us. So we have 50 plus 5 records. Okay, join of previous two selections over department. We have this much. Okay, and the cost of query, total query is how much? We have 1,000 from employee table, plus we have this 1,000 plus this 50 and this 50, this 50 and this 50, 2 multiplied by 50, plus 5, this 5 and this 5, and then we have 50 plus 5 together. So how many record IOs are needed here? 11,660 record IOs, which is lot much lesser than your first query RE expression. You know, now did you understand? This is the first query. This is the second algebraic expression for the same query. This is the third way of writing. And there is lot of difference. There is lot of difference in each one of them. Okay. So again, coming to this first slide, this is very important slide, because if you understand this procedure, then you are done with the query optimization. Okay, given an SQL query, writing different relational algebra for it, different relational algebra for it, and selecting the best one. So we know how to write the first one. How did we write the second one? How did we write the third one? First one, we use cross product. Okay, then we selected managers and names, and this is how we got more than 1 lakh records IOs. And in the second one, we changed the cross product to the join, and then we selected managers and sales out of it. In the third one, we selected the manager and the sales department first, and then we perform the join, and hence the workload is decreased a lot. So here we did not check everything, every row. We just only pick up the managers before the join. So it becomes very much faster. Okay. So now did you know how to write the same SQL in different RAs and calculate the cost of each RA? RA means relational algebraic expression. Okay. So Okay, now this is one of the array here. This is another array here, and then we are just drawing a tree for it. So this we covered how to write different algebraic expression. Now we covered this one also. Okay, then now the last part, which will give you marks, is for drawing the query tree. Once we have the relational algebraic expression, it is very easy for us to draw the query tree. Okay, so it's something like this. SQL given to you, you write RA, and then you write different RA. Okay, 1, 2, 3, whatever. And then for each RA, you draw the query tree. Then you draw the query tree. Then you draw the query tree and you select the best one. Okay, so we have done with this part. With this part, now we have to see how to draw the query tree. Okay, this will solve this question completely. Okay. We'll come to that point. So I hope you understood this all part. Now, a quick recap of the query execution. We discussed about the query execution in detail in query strategies for executing queries. Okay, steps in query execution. You give the high-level SQL query to the DBMS, okay? And then the DBMS performs the scanning, parsing, and validating that the query is written correctly. And then it translates into the immediate query, which is nothing but a logical query plan tree. And then the query optimizer selects the best execution plan, and the query code is generated for this execution plan. So the output of code generator is code to execute the query. And then this code to execute the query is given to the runtime data processor, which gives you the result. So this is the flow chart that actually depicts the high-level process of how the database management translates a high-level query written in a user-friendly language into series of operations that is to be executed to get the desired data. Okay, so these are the steps that you need to follow in processing a high-level query. So you can get a question saying that write down the steps that are required to execute a query or steps required in query execution. So these are the steps. Okay. Now, what is this? This is called as a cost-based query processing pipeline. What are we doing here? We create a query, okay? Then the query is passed to the parser and translator, okay? And then a relational algebraic expression is generated. The optimizer selects the best plan by looking into the statistical data and then passes it to the evaluation engine, which consults to some data that needs some data or whatever, okay? And then creates the output for this query. So this all things are working in a pipe, one after the other, one after the other. Okay, and this is exactly what we did in the previous example. We were given the SQL query, okay, and then we created a relational algebra, and then we checked their cost, and we selected the best one to execute. So this all is done automatically by the the evaluation engine inside the RDBMS. So this figure is called as cost-based query pipeline in the relational database. In exam, you can be asked about a question about drawing the processing pipeline, query processing pipeline by using the cost. So this is the answer for it. You draw it and explain it. The explanation is also given in the slide inside the notes. You can check. Okay, so basically, what is this flow diagram doing? It is creating a cost-based optimization approach where the database management system will analyze various execution strategies for a query and chooses the best one that is expected to have the most efficient query to be executed by estimating its cost. Okay, let's move further. Talking more about the scanning and the parsing, this is the first step in your query cost estimation. In scanning, the query text is converted into tokenized representation, okay, which is again created which can be represented to a tree form, okay. The parser will check the tokens if they are written using correct syntax or not, and then it will bring the columns out of the tables that are required, okay, inside the query. And it actually uses some keywords and structures to create the a table. For example, after joining, we have a new table, right? The original table and the table that has been created after a join operation or a Cartesian product. So this is done at the processor end, at the parser end, okay, and then the query passes the parsing checks after the query passes the parser check, then it is passed to the query optimizer. Okay, so the query optimizer can now execute the best one. Okay. For a given query, there are a number of different ways to execute it. We just saw a given SQL was solved in 3 ways. Okay. So each operation in the query is performed by using select and join. Okay. Uh, or by using different access path or different access routines. For example, an access routine that uses an index to retrieve fewer rows could be more efficient than an access path or access routine that performs a full table scan. Okay, if you have an index on, for example, the employee table on employee number, this can bring you the employees faster. For example, if we create an index on the academic ID of the students, it will be much easier for me to reach to student who is having the academic ID as 101 rather than checking all the 100 students and then finding the student at 101 location. Okay, so index helps a lot. Okay, the goal of Query Optimizer is to find reasonably efficient strategy for executing the query. We have been discussing this, how it does. It does this by using heuristics or by using cost optimization. We solved by using cost optimization. And the remaining chapter talks about finding the best form of executing the query by using heuristic optimization. So there are 2 ways in which you can find out the best query to execute, or the query optimizer finds the best query to execute based on cost based estimation or based on heuristic estimation. We covered cost based just now, and then now we are going to see the heuristic optimization. Once the query optimizer finds an execution plan, then by using the execution plan, the code is generated as we saw in the flow chart. Okay, with the interactive session, the code is interpreted and it is directly passed to the runtime database processor. It is also possible for you to compile all the access path and store them for later execution also. Query process. Now let us see the first one, query processing stage number 1. We translate the query, we cast the query into different internal forms, which means we create different representation of the SQL query into some internal representations for suitable machine manipulation. The internal representation typically is chosen in the form of abstract, syntax tree, or relational algebra query tree. So SQL is converted into internal representation, and this representation is called as algebra. So as I told you, SQL is converted into RA, then RA is converted into query tree. Okay, this is the query processing stage 1. Okay, and then the best query tree is executed. That's it. The second, which will be the query processing stage 2. Okay, so as I said, SQL query is converted into the query tree by creating query blocks, which is written in relational algebra. Okay, so the SQL is translated into equivalent extended algebraic expression, okay, which is called as query blocks. Okay, then these query blocks are used or converted into query trees. A query block will contain select from and where clause. It can also have group and having clause. Optimizer will choose the execution plan for each block. This is our SQL query. Now, if this particular query is having two parts, it is having the inner query. The inner query is executed first. The result of inner query is supplied as a where condition for the outer query. So we have one query block for this. This is the query block. Another query block is this. Okay, so the SQL, this is SQL. Okay, these are SQL, sub queries, and this is your query block. Okay. Now, for now, let us see how to draw the query tree. Okay. When we are drawing a query tree, it is very important to understand the structure of the query tree. There is a root, there is intermediate operations, and then the leaves. The query tree consists of a root, leaves, and intermediary operations. In the leaves, we have the table names. Okay. In the intermediary operations, we might have operations such as cross product or join. Okay. So here in this particular example, we have a cost product, which is linking employee, which is, creating the link between employee and department. Okay. So employee and department. This is your intermediary operation. Cross product is your intermediary operation. Leaves are nothing but the table names. Root. What is a root? Root is actually this predicate and all these operations is nothing but the root. Based on your selection, you join the tables or cross product the tables, and then you represent it as an intermediary operation and the table names and the leaves. I hope it is clear. Okay, now let's proceed. Now, this is the query which needed how many operations? 1,01,050 record IOs needed, the first one. So, in this particular example, we are seeing how to translate the relational algebra, okay, into query tree. We have to think about the leaves, which are nothing but the table names. So, okay, let me do it all over again. So first decide who will be the leaves. So we have employee table, and this is our one leaf, and we have department table. This is another leaf. How are we joining them? We are joining them using cross product. Okay, so we join them using cross product. We join them using cross product. Okay. And after we get this, what are we trying to select? We are trying to select the job is equal to manager and name is equal to sales. Okay. And department is equal to department number. Department emp dot dptno is equal to department dot deptno. Okay. So this is our predicate. So predicate is written in the root. Predicate is written in the root. The where condition is written in the root. The way how we are joining the tables are written in the intermediary operation, and the leaves are nothing but the table names. Now the second one, you can draw by yourself. How many tables do we have here? Emp table and depth table. So they are becoming the leaves of our tree. Now, what are we trying to do? We are trying to join them. So the join operation is used. What is the condition of the join operation? This is the condition of the join operation. So we wrote it inside the intermediary operation. What do we want to select? We want to select the job names and manager names. Okay, so this is the representation of query tree for the second way of executing the SQL query, a given SQL query. How many, for your recap, I have also written how the join works. How many IO records have been needed to execute this query tree? 3,050, right? Now the second one, let us draw. Here we have emp table, we have department table. Now, what did we do? We selected only those employees who are managers. So we are pushing down the select into the intermediate reaction so that the number of records can be decreased. So we selected the department names, only those departments whose name is equal to sales, and only those managers whose name, whose job is equal to manager out of employee and department. So our intermediary operation is now our select operation. Okay, our select operation. And then after we get the answer, we are joining the tables. So the number of IO records have less decrease, significantly. Okay. So it is something like instead of selecting the whole section 65, you are just selecting only those students who got GPA greater than 4. Are we understanding? So you did this and then you made a join on it. So this is the query tree for the third relational algebraic expression that we created for a given SQL. Optimization. Efficient representation of query in converting by converting the internal representation into some canonical form by using heuristic rules. Okay, is helping us to convert to canonical form. What is a canonical form? Canonical form is like, for example, we have a one query, then it is optimized to the second one. Okay, then it is optimized further, then it is optimized further. So all of them are called as canonical forms. Different possible forms are called as canonical forms. Here we have seen three canonical forms. This one with this with this cost, and the third one with this cost. So they are all three canonical forms. Which is the best one? This is the best canonical form. Okay, so okay. Heuristic, using heuristics in query optimization. The main heuristic is to apply the first operation that reduce the sizes of intermediary result. Okay, for example, you use applying the select and the project before the join. This is what we did here, right? We applied the select and we applied the where condition before applying the join. This is the main heuristic. Okay, the main heuristic is to apply the first operation that reduces the size. For example, if there are 60 students in section 61 and only 4 of them got the GPA greater than 4. So instead of selecting 60 and checking 60, I can just select 4. So the condition is applied first, then the selection is made. If I make the selection first, then then execute the condition, then it is like 60 plus 4, or read and write overheads are needed. But if I execute the condition first, then the selection, it is going to reduce significantly. It is going to reduce greatly. So this is the first one. Okay. How do you process for heuristic optimization? You need the parser, you need the heuristic rules, and you need an execution plan. And this is the one of the basic rule for creating the best version of relational algebraic expression. Okay. So the second one, optimization of query tree. We know that the given query can be represented in many different query tree forms. Okay, for example, our SQL in the question, in the example, one SQL, 3 relational algebraic expression were generated out of it. So many different forms can be done. The task of heuristic optimization is to find the final query tree, which is the best. Okay, for example, in our case, this is the best one. So this is what the heuristic optimization is doing for us in the inside the DBMS. For example, now let us take another example. We want to select the last name, okay, from how many tables? From the employee table, okay. But who is working on a project called as Aquarius? Okay, Aquarius. And who has the project number, who has a B date as this. Okay, so we want to select the last name of the people working in the project called as Aquarius. and the birth date is this. How are we connecting this table with this table? See, we need to access the employee table for getting the last name. We need to get the project Aquarius from the project table, and how this employee is working on the project is by using the working relationship. So here we have 1, 2, 3 tables to give us the data, complete data. Hence, we need to make a link between these two tables, and which is done by using project number and SSN. SSN is inside employee table, foreign primary key. ESSN is working is inside works relation, and the project number is inside the project table. So we have this condition to link 3 tables. Okay. And we have this predicate and this predicate. Predicate means the where condition. Okay. And we have 3 tables to retrieve the data from. And actually, we want the last name for the employees who are working on Aquarius project and who are, whose birth date is greater than this given one. Okay. So this is our query. Now let us see how we work on this query. We have like how many canonical forms given here? A, B, C, D, E. Okay. So let us see how we make 5, how we draw 5 versions of query tree on them. Okay. Let's see. The first one, we know in the leaf we write, we put the table names. So you remember we have root, we have intermediary operation, and then we have leaves inside our query tree. The leaves are always the table names. Okay. Now, this is our table name. This is our table name. This is our table name. We are connecting employee with the works on with the cross product. Then the result of this is cross product with the project. So all these 3 are now linked together. Okay. Remember, cross product going forward will be replaced with the join operation because cross product generates many rows. Okay. So we are done with the leaves. Okay. And how the tables are connected here by the cross product. Okay. Now, the second thing is, this is our predicate. So we wrote the predicate. And this is the final answer we want. So this is the final answer. What we want is written inside the root. Okay. So again, the table names are given in the leaves. Okay. And how are we linking the tables? By using the cross product. Okay. And what is our predicate? This is our where condition. Okay. So we wrote the predicate as again a part of intermediary operation inside our query tree. And what is the final thing that we want is kept inside the root. So this is our root. Okay. So this is the root. Okay. This is one of the initial canonical form. Canonical form only means, a type of relational algebraic query tree. For example, if you have to solve a problem and there are 4 solutions for it, then it means there are 4 canonical forms of it. The best canonical form becomes the final answer. Okay. So this is one of it. This is the initial one. Initial one. Okay. Now let us look in the second one where we are trying to move the select operation down. We want to, move the select down. So you see, we have divided this predicate into number of smaller predicates, and we are trying to push them down. Instead of selecting all the employees, I will select only those employees whose birthday is greater than the given day. Instead of selecting all the employees, I will who is working on the project, I will select only those employees whose SSN is matching. Okay. And instead of selecting all the projects, I will select only those projects whose project name is Aquarius. So here, the initial intermediary, sorry, not the initial, the intermediary uh, conditions are the select statements. We move the select statement down the tree now. Then we are performing the join. Then we are performing the join. Okay. So it's like you're selecting first those employees whose birthday is greater than the given day. Okay. And then you are joining it with works on. Once these two tables are linked together, you are joining with the project table. But before joining, you are, before not joining, Cartesian product. Still, see, wherever we have cross, it means a cross product or a Cartesian product. Where we have join, it means we are joining. So in this example, we are still using the Cartesian product. But the difference between this tree and this tree is, it is first performing the cross product, then checking the condition. Here we are checking the condition first, then cross product. Checking the condition first, then the cross product. And finally, getting the last name out of it. Okay. So this is how it's done. So here also, after you join, you are connecting this whole table with the project by using the project number is equal to PNO and getting the last name out of it. So in the first canonical form, we we joined the table, we cross product the table, then we wrote the product, then we wrote the predicate, and then we wrote the root. So here the root is the final answer, what we want to see. Predicate is the condition, and the tables are our leaves, and join and the cross product is our operation. Okay. Now, I want you to take, I want you to now look into this and look into this and see what is the difference. Take 2 minutes and then see the difference, what is happening in each one of them. Read this for the 1 minute. Read this for 1 minute. Okay, now I will explain. Here we have a project table. Inside, okay, what did we do in the project table? We selected those project whose name is equal to Aquarius. Then we linked the project with the work on table by using a cross product and project number. We got some answers here. We got some rows here. Okay. Then then we are going to link this cross product table with the employee table. Okay. For only those whose birthday is greater than this given date. And whatever answers we have, we are going to link them, these two tables, the cross product of project and works on, linked with the employee by using ESSN. And then we get the last name out of it. So if you see, a slight difference here is we are selecting, you see here, we are selecting the project name later. Here we are selecting the project name first. Okay, this is possible. It is like saying select me, get me, you know, the product, the project numbers. Okay. Okay, see, students. Okay, for example, if I want to select the student name and the department name, there are only 4 departments, right? There are only 4 departments, but there are many students, right, in different departments. So if I select the student names, then select the department, there will be so many students. Similarly, if I select the employees, there are so many employees, there are 1,000 employees. But how many departments do we have? How many projects we have? Less number of projects. So we are selecting the less number first. Okay. So for example, okay. Okay, let me clean and explain you again. So, okay, let us take an example of department. Okay, IS, CS, CN, and computer engineering. How many departments do we have? Only 4 departments. Okay. And how many students we have? Many number of students, maybe 2,000 students we have. Now, if I want to select some student, okay, who is in CS department, I can check all the students, then check the CS department, right? So for example, here it will be 2000, okay, multiplied by 4, it will be, 8,000 scans are needed. But here, if I scan this 4 departments first, there can be only 500 students in CS department. So I go to the CS department first, okay, and I see only 500 students. I will not, check remaining 1,500 students. I will check only 500. So 1 multiplied by 500 is 500 scans are needed. So this is what we are actually doing here. We are, because the projects are less than employees, we are selecting only those rows whose project name is Aquarius. So that is why we are selecting the project table first, then we are joining it with the employee later on. Okay, so this is the now another improvement. Okay, this is another improvement. So we are selecting the project whose name is equal to Aquarius, and then we are linking it with the works on table. How are we linking it with, how are we combining both the tables? By using a cross product based on this P number is equal to project number. Okay, and whatever result we get, we are then joining with, then we are cross protecting it with employees whose birthday is greater than this date. How are we linking these two different parts? By using ESSN is equal to SSN and then getting a last name out of it. Okay, so this is, the fourth improvement. Now the next improvement is we are doing the same job, but instead of using the cross product, we are going to use the join, the join. Okay, everything remains same. Project works on employee, project works on employee. Okay, selecting the project with this Aquarius name. Okay, checking both of them, combining both of them by using join instead of cross product. Here we have join. Same thing, selecting employees with the birth date greater than the given date and connecting them both by using a join instead of a cross product, and then selecting the last name. This is the another variation, another canonical form. Now the final one. Now please take a look at it, detailed look at it. Look at this, stop the video and try to notice this for 1 minute. Now here, what we were doing, we were, having the condition P is equal to Aquarius. Okay, and here B is equal to greater than this, and SSN, we are joining with them. So here what we are doing is we are selecting P name, project name as Aquarius. Okay, where project name is Aquarius, where ESSN is equal to product, number. This is an extra thing, and birthday is equal to this. Okay, so okay, what is this? This will select the rows which will have where condition. Okay, and this will select the column. So what we're doing here is we have project works on an employee table at the leaves, no change. But here we are selecting the where condition, and soon after that we are selecting the project number. So we are saying that get me the rows whose project name is Aquarius. Okay, for all of them, get me the product number, the project number. So that I can, here also select ESSN and project number, and then I can quickly compare this here, and it will give me ESSN here. Okay, so it's like you are making a select. This one is called as project. Okay, this one is called as select. So you are actually projecting the column, ESSN, and projecting the SSN and name soon after you are checking the condition. And then you are linking these three tables, okay, connecting these three tables at the higher level by using their ESSN is equal to SSN, and then getting the last name. So what is the extra step here? If you see, the extra step here is this one, and this one, and this one. Okay, which is not present here. You see, we just have selected the last name. Okay, in the root we have only last name, but here we have we have made, this is called as selecting the columns. So in here we only selected last name, but in here we are selecting SSN also, SSN also, ESSN also, last name also, P number also, and the project number also, and then the final last name. This is the fifth heuristic. 5 queries you see, we have, moving the project operation down the key. So this project have been pushed in the down. First we pushed the select, but in the last one we also pushed the P number down. We select the P number down. Earlier selection of P number is done here. Now it is much before that here. Okay, so given query here, this query, how many query trees did we just draw? 5 query trees we have drawn. Okay, out of this 5, the first, second, and third were drawn by using cross product. Okay, and the first one, all the predicated result is written in the last but one root, and here they were divided. Okay, in the second one. The third one, we push down the row. Okay, we push down the row. In the fourth one, we push down the row and then we perform join. In the fourth one, we push down the row and we perform the join. In the fifth one, we push down the project also. Okay, so these are 5 ways of creating the query trees by using heuristics. Okay, now let us understand the transformation rules of RA. These are mathematical rules, like, for example, conjunctive selection. Okay, means, we have here to select PQR from a relation R. Okay, it is equivalent to say select P, select Q, select R from R. So it is like you are selecting first R column from the table R. Then you are selecting Q out of it, Q from it, and then you are selecting P from R. So it is equivalent to say select P and Q and R columns from the table R. For example, here the table R is emp. Okay, and P, Q, and R are, salary and department number. So saying select department is equal to 10 and salary greater than 1000 from employees is equivalent to say select department numbers. It is equivalent to say take out salary 1000. Get me all those columns whose salary is greater than 1000. Okay, wait, let us do it again. So we have an employee table. Okay, inside an employee table, this is your emp table. You have many fields. One of them is salary, another one is department. So you have many rows here. So this one, now not talking about the RHS, it is saying that get me the salary, get me all the rows whose value or whose salary is greater than 1000. Okay, once you get all these rows whose salary is greater than 1000, you are applying one more condition, which is telling that get me all those employees whose salary is greater than 10,000 and whose department is equal to 10. It is same as saying that opposite way. You are saying select me first all the department who is 10, then select me all the rows. Uh, a condition which says that the department is equal to 10 and their salary is equal to 1,000 out of this. Okay, so it means that if you want to have conjunctive selection, okay, a big conjunctive selection, it can be divided into cascading select operations when you have the attributes of the same table. Okay, attributes of the same table. So bigger and can be processed like this, one after the other, when you have only one table and many fields out of it to be selected. Okay. The second law, commutative law. If you want to select a column P and Q from R, you can select, it is equal to select Q first, then P from R. For example, you are trying to select salary greater than 10,000. Okay. And the department, okay. How this will be executed? See, whenever you have the query, algebraic query expression, you start executing from this part. Okay, so you have an employee table. Out of this employee table, you have selected only those employees whose department is 10. And out of this, you want to select only those employees whose salary is greater than 10. This is equivalent of this query. First, here you selected salary out of salary greater than 10. Then you are selecting department number of 10. The query set, the result is same for both of them. So this is called as commutative of selection. Okay. Now, in the sequence of projection, if you have series of projection, okay, the first one is important. The first one is important. Okay, for example, here you have to select DPTNO and rename, okay, columns. Yeah, so you are, selecting without any condition. It is equivalent to the first one is important. So it is, this is equal to DPTNO of department number. So the first year will be here. The first year will be here. In the sequence of projection operation, only the first in the sequence is required. This is required. Commutative selection. Here we have commutative of selection and projection. You have column AI till AM. Okay, these are your predicates. Many selections, for example. If you have to project the attribute 1, attribute 2, and the where condition is P on R, then it is equivalent to say this out of the bracket first and then putting all the projections inside the bracket. For example, here your LHS is equal to RHS. You're selecting the name, okay, and the job where name is equal to Smith. Okay, you can even write it like this. Name is equal to Smith, then select name and job for it. It is same. Okay. For example, I want to select a student, Sarah. Okay. And I want to know her grade. Okay. It is equivalent to select the name and the grade where name is equal to Sarah, or select name is equal to Sarah, then get the grade and the name for her is same. This is called as commutative of selection and projection. Commutative commutativity of theta join. Theta join and the Cartesian product. Okay. Theta join is it's a form of a join, okay, but which combines the natural join plus equijoin also. Okay, the commutative, it says that the table R join with S is equal to S join with R, same. Cartesian product R join with S table is equal to S table Cartesian product on R. Okay, this both are same. You write it here or you write it here, it means same. You write it here and write it here, it means same. Commutativity of selection and theta join. Again, we want to select something from the Cartesian product of RNS. Sorry, the join of RNS is equal to selecting it from R and S in the same time. So you select from join first and then make a join with S is equal to selecting them before the join. Okay, when you have the table like this, where selection predication P is only made up of join attributes here. Okay, so here we have an example like this. Select the department number equal to 10 from employee, okay, is equal to writing like this. Okay. Commutative of projection and theta join. You have R and S table as join, okay, and then you are trying to take out an L attribute out of it. It is equivalent to take out the L attribute from R, another attribute from S, and then perform a join on it. It is same, okay. Example, you're trying to take out job, location, and department number from employee, okay, and department equal to this. Based on this condition, you want to select job, location, and department number. It is equivalent to say, select me the job and department, okay, based on this condition, and select me the location out of this department number. So the department number is moving here. Sorry, the location is moving here in the second query. This is same. Okay, for example, this L2. Commutative of union intersection, R union S is equal to S union R. Okay, and R intersection S is equal to S intersection R. Commutativity of selection and set operations. You are selecting the predicate rows. You are selecting the attribute base, from the union of R and S is equal to selecting it from S and selecting it from R, and then performing the union operation is same. Intersection also works like this, and difference also works like this. So if you want to select the attribute P, okay, from R minus S, is same as selecting from S, then minusing it from selecting, uh, of R. Commutative of projection and union, when you are projecting the attribute L from R union S is equal to selecting it from S union R. The places are changed, and then you're performing for this operation and union this operation. Associativity of natural join. If you have three tables, R, S, and T, and then you perform a natural join, it is equivalent to have R, okay, join before. How do we read the, we do the bracket first, right? So we join S with T, then the resultant is joined with the R, is equivalent to join R and S first, then join it with T. Cartesian product also works the same way, okay. And associativity of union. If you union R and S table, the result you can make it union with T is equivalent to make R and T union first, then make the union with S. Similarly, intersection also works like that. So heuristics, we have how many heuristics? We have 6 heuristics. With each heuristic, you can have one query tree. For example, break up the select operation with conjunctive condition into cascade condition. This is what we did here, right? We have a big condition, then we divided this condition into smaller condition, and then we kept on pushing them down. Okay, so okay, then using the commutative select, move each select operation down the tree. Then using the commutative and associative of binary operation, rearrange the nodes and the leaves. Then combine the Cartesian product, change it to join operation. Okay. And using the cascading project and commutative project, computing of project, other project with the other operations, break down the projections also down. Okay. And then identify subtrees that represent group of operations and that can be executed by a single algorithm. Okay. So these are the 6 things that we do in the heuristic based query optimization. Now we have a query form. Okay. This is the first form where we used the cross product and we're trying to take out the managers from the sales department. Here we want to select the manager from the sales department, but we want to connect emp and dep table with a join. Here we want to select only managers and select only sales department, and then the result is smaller here, right? For example, here 50 managers are there out of 10,000, out of 1,000 rows. Okay. And here out of 50, we have 5 only. So we selected this 50 and 5. Then we made a join operation. So this is the best canonical form. Okay, so here we have another example. Okay, let us do this example. Let us understand what is being asked here. We want to select the renters who, we want to select the renters, sorry. Let me select the pen. We want to select the renters, the color. We want to select the renters who are looking for flats. Find the properties that match the requirements, are owned by CO 93 owner number. So we can write the SQL query like this: select p dot property number. Girls, you will be given the table structure, okay, when you are being asked a query like this, so that you can make the SQL by yourself. So select p dot property number and p dot street. From how many tables we need this information? From client table, from viewing table, and property table. So we have these 3 tables connected with each other by using the cross product. Okay. How many columns do we want to select? We want to select the property column and the street column. So whenever we want to select the columns, we use project. Okay. When I say project, it means selecting a column. Okay. So we want to select property number and property street. So we use the project p dot property name, same, just change this select with the project sign. This is select. When you have where condition, whenever you have this where condition, you are going to replace it with this row. Okay. So this is done. These 2 things we transferred here. Okay. Where condition. Okay. From is, from comes here. And we want, this is our predicate. This whole is our predicate. So this is our where condition. We are just using a row with this first, and we are replacing this and operate with the intersection. So we have intersection here, we have intersection here, we have intersection here, and we have these all predicates written one after the other. Okay. Done. Next move. So applying the first rule and the second rule and the 6th rule to split the number of selection into individual selections. So we have C and V cross, and then both of them are crossed. We have it like this only, right? C and V cross, and then both of them cross with P. C and V crossed, both of them cross with P. This is clear now. Now here we have all the predicates, all the where condition. And what do we want? We want to select only 2. This becomes our root. So this is our primary, the initial canonical form of our query tree. The second one is we are splitting this now into individuals. Okay, this is individual, this is individual, this is individual, and this is individual. And then pushing them down till here. So C cross V, but we are only selecting the flats with the type equal to flat, okay, from the client table. cross multiplying with the connection of how we are making the connection between the V table. Okay, this V table, viewing table, client with viewing table with a number, client number, and then with the product table, uh, property owner table with this condition. And then dividing this bigger one into smaller predicates, and then selecting the property number and the street. If you notice here, what did we do? If you notice here, what did we do? We have divided this and pushed them down for their corresponding table so that we only take out not all the rows, but we take out only those rows that satisfied our condition from these tables. Okay. And then we join their result, we cross product their result, and then we take out the final condition and the columns out of it. Okay, so now one more very easy thing to remember, how to, make this all, or how to distribute this is, see, um, we have C table and V table. They both are going to be connected, right? How are we going to connect them both? We are going to connect them both by the client number in V equal to the client number in C. So this is used to connect these two tables. Okay. But this one we push down because we don't want to connect all the table. We just want to take out the required fields whose type is equal to flat. Then only we want to connect this. So that is why we push down this row down we push down this predicate, which is nothing but the where condition, select where condition, down to the table. Okay, so we are just picking up only not the complete table but only those rows which property type is equal to flat. So we are connecting client with view by using the cross product. How are now this is our result. Okay, and this is another table that we have to connect. So we are going to connect them here by using this condition and this condition. Okay, the property whose property number is this and the client is this. So the client is matching with this property. It means the requirements of the client is matching with this. So both of them are connected. Okay, so the property, connecting these two things by using property numbers. And then we are saying the maximum rent and the property type. Okay, so these are the two conditions and conditions, okay, which will say that the maximum rent is greater than or equal to the property rent and the property type is equal to flat or property type from the other table. And then we are selecting the property number and the street. Okay. Now, another one, what we are doing is we are replacing all these crosses with projection here. So you see projection, projection, projection here. And this remains the same. This remains the same. This remains the same. Now here, what did we do? Here we have reorder the equijoins. So CVP, we are now taking not all the clients, but on the product, the properties table first, then the view table and the C table, and other things remains the same. Now here we have pushed down the selection also down. This is the new thing. Here we were just taking the row, okay, down, but here we have the select select is nothing but project, right? Pushing down the or sending down the projection down. Okay, so here we have this new thing. Okay, other things are same. Instead of cross product, we are using the join. Okay, now yeah, so here we want to select the property and street, okay, where the maximum rent is greater than P rent and client number is equal to client number. So here we are putting only one condition. We are sending down another condition here. For example, here this we are sending down the other condition here. You see here, here we have property type and property rent. So property rent we kept it here, and we sent down the selection for flat still further. So the selection is done first, then the join is performed, and then you take out the final one. Now, if you see this question, draw at least 2 query trees. Now you know how to draw the 2 query. We have been drawing 6 query trees, right? Just now. So this is the given SQL. You will transform it into relational algebra and it will give you this. And then using the relational algebra, we have pushed down the products, project table, department table, and employee table here. Okay. And then we have used, it's working this way. It working? Wait. So this is the first one. This is actually the first one. Okay, so this is the final. This is the final one. Okay, and this is the initial one. So you draw the initial one first. We have product, we have the department, and we have the employee table. They are cross product, and then the predicate is written here. And you are selecting these columns. So what did we do? We are pushing down this predicate to the corresponding tables. So this predicate is sent to the project. This predicate is sent. Okay, this predicate is sent here, and Stanford, and okay, and then we selected the department from, okay, so this is joined. Project table and department table is joined here. The result of this is joined with the employee by using this condition, and then we are selecting all. Okay, so these are the two things. You can still divide it, keep on dividing by sending this down, right? Like we saw in the 6th, this one, sending this down to the corresponding tables. Okay, so done. 2 query trees are there. Many query trees, for example, I can draw one more query tree wherein I will select this P number here, D number here, and E here. Okay, and I can select, join them and select the B date as a final one. So these are the minimum 2 trees that we draw. And here, select F name, last name. This is another example. We have a select query. Okay, so we have represented it by using the union. Okay. F name, E name is your last address. Okay, this example is showing that the given SQL can be written in another way by using union. So when I have to say select the first name, last name, and address from the employee table, where D dot name is equal to research and D dot number is equal to DNO, I can do it by selecting the first, okay, union this. And I am removing this R, D dot D name is equal to research and D dot number is equal to DNO. I am removing that and I am selecting the project number, project department, employee. Okay, so sorry. This is altogether a different one, not the same story. Wait. So here what we are doing is we have one query, example query. You can draw the query tree for this. We have another query by using union. Okay, you can draw the query tree for this. Okay, then that's it. In the exam, you might get questions like this. Discuss the reason for converting SQL queries into relational algebra before optimization is done. So why do we convert SQL queries into relational algebra? To find out the different ways in which SQL query can be executed, right? What is the query execution plan? What is the query execution plan? Query execution plan is this side. Mm-hmm. Yeah, the query could then be chosen by for each block. Okay. This is about the execution plan. Okay. And another question can be, okay, what is meant by heuristic optimization? We just saw there are 6 heuristic optimization. You can name them. Discuss the heuristics that are applied during query optimization. All 6 of them you can give here as an answer to this question. How does a query represent a relational algebraic expression? You can give one example how the query tree, write an algebraic expression and give its query tree representation. That's it. What is meant by execution of a query tree? Okay. Discuss the rules of transformation of query trees and identifying each rule should be applied during optimization. This is your transformation of, for example, this one, these all, your, these are transformation rules. And how did we apply this in the query tree? For example, here we have a big predicate, right? We have conjunction of and operators here. We split them down into single ones, right? So you can, and then we push them down, the select and the project near the tables. So this is about the query optimization using 2 techniques, using heuristics and using the cost estimation. So we talk about query processing. We talk how to translate SQL queries into relational algebra. We saw 1, 2, 3 examples. We saw one question also in the final exam. And then we have using heuristics in query optimization. Okay. So there are how many? 6 heuristics were given, right? So you can use them. Okay. So what are the 6 heuristics? These are the 6 heuristics. Okay. So that's about the query optimization part 1.